Good afternoon, students. So, we will basically start off from where we left in the last class, where we showed that the entropy of an ideal gas can be written as well. We derived an expression for the number of accessible microstates for an ideal gas at NVE conditions as this expression. And we remarked that the n factorial here purely stands for the fact that the particles of a gas are indistinguishable, and hence for each microstate there was a serious overcounting by a factor of n factorial, that is the number of permutations you can do with n objects. So, purely respecting the fact that we want to only take the microstates where duplication is not permitted, we have to divide the entire number of microstates with n factorial, and this division by n factorial actually makes the entropy purely extensive. As we shall see, we did derive the expression for entropy, and I am going to write down the expression for the entropy by taking a logarithm. So, you can compute the entropy, which is kb ln omega, and this can be seen very easily if you take logarithms assuming n is very large. Then you can write it as n kb logarithm of EV over n into 4 pi m e capital E over 3 n h square to the power 3 half. Now, this derivation of s from omega, we have assumed that n is very large, which means I have taken 3 n by 2 minus 1 as just 3 n by 2, and hence I have taken factorial 3 n by 2 as just 3 n by 2, and the logarithm of 3 n by 2 factorial minus 1 is hence just a logarithm of 3 n by 2 factorial, and this has been taken to be from Stirling approximation just 3 n by 2 ln 3 n by 2 minus 3 n by 2. Okay. We have also dropped terms like ln n, ln e, etc. in comparison to n ln n or n ln e. So, these terms are much larger compared to these terms which we have taken to be as almost negligible, okay, because you can simply see that if I take n as a large number, let us say, then ln n approximately goes as 4. If I take ln 10 to the base e as 1, it is close to 1, but n ln n is approximately 4 into 10 to the power 4. So, I am definitely going to drop ln n in comparison to n ln n. Okay, so, that is the reason why I have dropped several terms in taking logarithm. Fine. So, let us go back to our expression for entropy, which is a nice beautiful expression sitting here. So, I am going to just copy this expression Okay. So, let us so I am going to copy this expression to a new page where I am going to do something with it. All right. Like I said in the last lecture that I want to do some thermodynamics on the system. So, the route to thermodynamics is often laid by this bridge between microstates, this beautiful expression given by Boltzmann, and that this is the microscopic world or microscopic information, and Boltzmann's bridge connects this with a thermodynamic or macroscopic observations. So, this is a beautiful bridge that connects the microscopic world to macroscopic worlds. So, let us take advantage of this bridge and construct quantities that we require. So, if you recall the first law of thermodynamics, you can say that you can write down okay. So, I am going to write down the first law of thermodynamics as TdS, the heat given to the system, equals to the change in internal energy plus work done by the system. It may expand, and let us also include some chemical work or minus mu dn. Okay. Now, mu here is the chemical potential. So, if I want to compute the energy of the ideal gas, so I can use this expression and write down, get an expression for energy by simply saying that T ds over dE at constant value of V and N should be 1. Okay. Just take the differentiation with respect to E, keeping volume and number of particles constant. So, you will see that this will go to 0 and this will go to 0 because N and V are taken to be as constants, and what you get on the right hand side is just 1 because you have taken derivative with respect to E. So, this will give us T times if you look at your entropy expression, taking derivative with respect to E will give us nothing but N Kb over E equals to 1, and there will be a factor of 3 by 2 which is precisely this factor. Okay. So, if I take logarithm of e raised to 3 by 2, it is just 3 by 2 logarithm of e. Okay. So, what I will get here is basically 3 by 2 into 1 by e, okay, because logarithm of e's derivative is 1 by e. So, this will give me the internal energy of a gas as 3 by 2 N kBT. That is the expression for the internal energy of a gas. Perhaps you knew it already from kinetic theory, but here you derived it using statistical mechanics. So, another result you can obtain is the relationship between pressure and temperature. Now, here in this case you take from the first law at and you take the derivative at constant E and constant N. Okay. So, when you do that, you basically you are doing you are taking the derivative of S with respect to volume at constant energy and number of particles, okay. And that will simply give you T times, if you look at the expression of entropy, taking derivative with respect to volume is simply giving you NKB over V, okay, because everything else is a constant and does not depend on the volume. So, it just gives you T times NKB over V, but this is equal to, if you look at the first law, this is equal to pressure, okay, from first law. So, you get the ideal gas law as PV equals to N KBT, okay. So, this is the equation of state for an ideal gas derived from statistical mechanics, and we are now in a position to generalize our argument of the entropy of an ideal gas to mixing of two gases. So, this is the this is an important subject. So, I am going to simply take this expression here, okay. So, I am going to talk about a new subject, which is mixing of two gases. Right. So, I am going to basically construct an experiment quite similar to the Gedanken experiments done by Gibbs when he was puzzled by the entropy increase that accompanies mixing of two gases. He did two types of experiments, thought experiments. One was mixing gases which were of the same type, and he did an experiment on mixing gases of different types. So, in quite surprisingly, he found that when you mix gases of the same type at same temperature and densities, if you do not properly account for indistinguishability, this mixing apparently leads to rise in entropy of the universe, which is wrong, because when you are mixing two gases at same temperature and density and the gases are of the same type, okay. Suppose you mix oxygen with oxygen at same temperature and same density, then this mixing leads to no rise in overall entropy of the universe, because if you look at the system after a long time has elapsed, you cannot distinguish the macro state after you have mixed with the macro state that you had in the beginning of the experiment, okay. So, we will discuss this these two different cases, and I am going to talk about the first case when two different gases are mixed. Okay. And let us, for the simplicity, you take the density and temperature to be same at same rho and T, just to keep things simple. So, I am going to draw this schematic. You take one gas in a container, call it gas of type A, and you indicate A type particles with or I think it is even better if I take let us take circles. And you take in another chamber gases of type B. Okay. Now, if if you see that these particles are of different types, so let us say there is a shutter here in between which can be opened and closed. Okay, so I am going to basically indicate this shutter by a red line, let us say. Okay, so this is a shutter that can be open or closed, and I have started for the case of for the case of simplicity, you know, n1 particles on this side, n2 particles, and I have taken volume V1 and I have taken volume V2. I have taken the temperature to be same and I have taken the density to be same. So, the rho here is N1 by V1 and the density here is also the same. Number densities are taken to be the same. So, if you open the shutter and wait for long times, so what do you see? What will you see after you come back? Let us say you go for a cup of coffee and you come back after a long time, what will you see? There are two different gases at identical temperature and density. So, the shutter has been opened. So, I am going to just to indicate that there was a shutter here, I will draw a virtual line, and what you will see after a very long time is that these two systems have mixed. Okay. And I am going to ask you one question, is this mixing reversible or irreversible? Meaning, can I recover my old system A and B? The two gases have mixed, I cannot put the shutter back and recover my old system. Okay. So, what you have seen is basically a mixing that is purely irreversible. So, I am going to conclude that this is an irreversible mixing, and we know that the entire system A plus B is mechanically and thermally isolated. Okay. So, the entire system is isolated from the surrounding, completely isolated, which means no amount of heat is exchanged and no amount of work is exchanged, and particles also cannot escape. So, no heat can come in or leave the system, no work can be done on the system, and certainly particles cannot escape. So, complete isolation, and what you have seen is that in this isolated system something irreversible has happened. So, it is well known from the second law of thermodynamics that I must see the total entropy of the universe to increase. Okay. It is in fact greater than 0, the equality should not be there, and I will call this as the entropy of mixing. Now, what is delta is here is basically the entropy of mixing or the total entropy difference initially and finally. Okay. So, this delta is nothing but the entropy of the final configuration minus the entropy of the initial configuration, and this is a positive number. We can calculate this. So, and this delta is precisely is called as the entropy of mixing. Okay. Now, if we recall this expression for entropy, so I can use this expression here. Okay. So, I can use this expression to compute the entropy of mixing. So, you write down the initial entropy first. Now, initially what you have is basically these two gases A and B. So, you write down the entropy of these two gases and add them up. So, initially the entropy using this expression for the A type particles is simply N1, because you had N1 particles, into Kb into Ln. I am going to write down E by rho 1, because N1 by V1 is rho 1, into 4 pi M1 E1 by 3 h square N1 to the power 3 by 2. This is just the entropy of first gas. Okay. I can in fact take Kb constant outside. No, this is just SI, initial entropy. So, initial entropy I am taking the sum of A and B, plus I am going to write down the entropy of second, which is N2 ln E by, and since the densities are the same, I am going to write down just rho, okay, because rho 1 and rho 2 are just rho. So, I think for the presentation it is better to write down Kb multiplied to each one of them, it just improves the presentation. So, I am going to write down shift this entire object towards slightly on the, okay, and I am going to write down. So, this is basically the entropy of the A, plus I am going to write down the entropy of the system B, and this is initial entropy. Okay. This would be Kb into particles ln E by rho into 4 pi M2 E E2 by 3 h square into to the power 3 half. Is it fine? This is for the B. Okay. So, right. So, now what we can do here, we can write down the final entropy also. Finally, if you look at the system here on the right hand side, the n1 particles of A now have access to the entire volume. So, if I call that the final volume is the sum of the initial volumes, which is V, V being the joint volume of the two boxes. So, I can see that my zeros and the crosses are both occupying volume V. So, if I want to write down the final entropy, the same expression gives me the expression that I have written here for entropy, gives me N1 ln E by I am going to write it as E by N1 into total V into 4 pi M1 E E1 upon 3 N1 h square, or I am going to write it as h square into N1 to the power 3 half plus for the second system B system Kb into ln, but now it has access to the full volume divided by into 4 pi M2 E E2 over 3 h square into whole raised to 3 by 2. Fine. So, this is now the entropy of A and B. Okay. So, to compute the difference entropy of mixing, I have to subtract the final entropy minus the initial entropy. Fine. So, you can clearly see there are a couple of terms that I can straight away cancel. So, the term that I can straight away cancel from these two expressions is the, well, I can straight away cancel the log E and log E raised to 3 by 2 terms, because both have the prefactor Kb and 1. Okay. So, if you look at the expression, I can from the A types I can simply write down Kb N1 into ln into rho, because it is minus of Si and it is already ln 1 by rho, and from the second term everything else cancels. From the second term I can write down Kb into ln V by N2 into rho, because the SI component is minus of ln 1 by rho, which is already ln rho, and that is it. Everything else cancels, because if you look at here, for example, this m2 to the power 3 half, well, it simply becomes 3 by 2 ln m2, and the prefactor is kbn2. Numerator in upstairs, if you see, there is one more kbn2, and that is also multiplied to 3 by 2 ln m2. So, all these terms will cancel. What you will have in the end is just this expression, wherein I can simply write down one more step. If I take kb outside, this simply gives me n1 ln, see, rho is already n1 by v1. So, this becomes v by v1 plus n2 ln v by v2, okay. And as you can tell that v is greater than v1 and v2, v over v1 is a number greater than 1, which means logarithm of v over v1 and v over v2 is greater than 0. So, SF minus SI is a positive quantity. So, what we ended up showing that delta S mixing is a positive quantity, and it should be, because my final configuration is a state of irreversible mixing. Look at the crosses and the circles. There is no way I can recover my initial system where crosses are sitting in one compartment and circles are sitting in the other compartment. So, by the pure nature of the mixing, there will be a positive entropy of mixing. So, basically I will say that my entropy of the universe has increased, okay. So, the total entropy of the universe is precisely increasing by a factor delta S mix, okay. So, if you want to understand what is meant by this argument, it is like I can say that the entropy of the change in entropy of the universe is nothing but the change in entropy of the systems plus change in entropy of the surrounding. Now, nothing happened to the surrounding is basically shielded. See, I have shielded A plus B, this means that I have shielded the surrounding. Now, nothing that happens inside my A plus B influences the surroundings. The surroundings entropy has not changed, okay. In fact, if I come back after my cup of coffee, the surrounding looks the same, nothing has happened there. But my system inside, which is enclosed inside isolated boundary, or a boundary which isolates my system, then I see that delta S of the system has become positive, and so this is in fact greater than 0, which is what we have observed. Fine. So, now we will take a different case, the case of mixing two same gases, okay. And as usual, I am going to take the case of ideal, this is the case of mixing when the temperature on both the sides is same and the density on both the sides are same. So, now I am going to do this experiment. So, as usual, you take two compartments and you take particles of the same type on both sides, because I am mixing two gases of the same type, and I have taken N1 particles in 2 particles. The volume of the container here is a V1 and the volume of the container here is V2, and I am taking the density to be the same. So, both sides I am taking density rho and I am taking the temperature to be the same. Okay. So, if you are taking the energy as E1 and the energy here as E2, well then this is nothing but 2 by 3 N1 okay, and the temperature here is 2 by 3 E2 over N2 kb. Okay. So, in some sense keeping same temperature on both sides means the energy density is same, E1 by N1 is the same as E2 by N2 on the other side. Now, again as usual we have the shutter here that we can open and close as per our wish. So, I have my shutter here. So, I am going to open the shutter and allow the gases to mix. So, basically I will wait for a long time. Allow them to mix. So, when I come back after some time, so what do I get? You might have already guessed it. So, if I come back after a long time, let me draw a virtual vertical line just to remind us that there was a shutter here before we went for a coffee, and what you see is basically A type particles uniformly spread across the 2 compartments. Now, I am going to ask you a simple question. The final volume is V1 plus V2, which is V. The final density remains the same and the final temperature is also the same, because you did nothing to the temperature and densities, the temperature density on both sides were the same. So, they remained the same after you have mixed it. Well, if you want to see why they remain the same, is simple. The final density is nothing but the final number of particles divided by the final volume, right. So, you just take the numerator, multiply by 1 upon V to both the terms. So, you take V1 into N1 by V1 plus V2 into N2 by V2 divided by V1 plus V2. This is just N1 by V1. If I take it as rho, it can be written just as it remains the same. So, it is either N1 by V1 or it is N2 by V2, which is nothing but your rho. Okay. So, N1 by V1 is rho and N2 by V2 is also rho, like I have taken here. So, I can substitute rho from both sides. What I get is rho plus rho divided by 2. So, it is just rho itself. Okay. So, fine. Okay. So, you can see the right hand side. So, it yeah. So, you can take V1 into rho plus V2 into rho divided by V1 plus V2, which is just rho. Okay. So, the final density does not change, remains the same, and the final temperature also does not change, because you can write down the final temperature by the same logic that it is 2 by 3 into total energy, which is now sum of the two energies divided by the total number of particles, which is the sum of two particles, divided by Kb. And since E1 plus E2, the same logic like N1 plus N2 divided by V1 plus V2 did not change, it remained N by V1. Similarly, E1 plus E2 divided by N1 plus N2 remains as E by N. So, this remains as E by N1, or it remains as so the final temperature also is the same. Okay, you can do the same trick. You can multiply the first term by 1 by N1 and the second term by 1 by N2, and just the same trick. So, now when you look at the final configuration, when A plus A has been mixed, you see that this is a reversible scenario, in the sense that the final, I am going to write down here, this is a state of, it is completely reversible mixing. Because I cannot distinguish between the final macro state and the initial macro state. No distinction can be made here. The system is this in the same macro state. Okay. So, when that has happened, you cannot tell that the system's entropy has changed. Okay. So, this configuration, after you have waited for a long time, is in the same state, and you cannot distinguish that an experiment has happened, okay, by any test or any investigation. So, clearly the final system is in a completely reversible, this entire change is completely reversible, and you do not expect any entropy difference to have arisen. So, clearly when your macro states hasn't changed, you do not expect any, you remain at equilibrium, you are in equilibrium to begin with, you are in equilibrium now. So, you have not gone away from the equilibrium, which means the entropy has not changed, the system is isolated, and the configurations are indistinguishable. So, you can check it from your expression. So, if you write down your entropy here, so I am going to write down, let us take this okay. So, I am going to, I just want to copy this expression. Okay. So, just recalling that this is the expression for entropy, you can compute the total change in the entropy. So, as usual you write down the initial entropy, which is the sum of two entropies of A and B. So, our particles of were now distributed, A type were in compartment A with volume V1 and B type were in compartment B. So, we can write down as N1 Kb ln E V1 by, we can write down V1 by N1 as simply E by rho into 4 pi m m1. Yeah, I am going to take m1 for both of them. E1 by 3h square n1. Fine. This is for just A type, for just one compartment, okay, plus N2, but because the compartment volumes could be different. So, we are taking A type in both the compartments, the compartment volumes could be different, which means the number of particles in the two compartments may be different, because you are keeping density the same. So, we are going to write down as Kb ln E by rho 4 pi m1 E N2, because the masses are same, upon 3 h square N2 to the power 3 half. Fine. This is for the B type. Okay. Before we open the shutter. After we opened the shutter and waited for a very long time, so the final entropy becomes now you have N1 plus N2 sitting in volume V1 plus V2. Okay. So, here it is going to be just N1 plus N2, that is going to be a total number of particles, but they are of the same type, multiplied by Kb E V by N is simply rho, because that has not changed the density, into 4 pi m1 E upon 3 h square. Now, you can write E1 by N1 or you can write E2 by N2, it is the same thing. Okay. So, I am going to write down as E1 plus E2 divided by N1 plus N2, with the realization that the two are the same, is the same as the individual density. Now, this is the final entropy for the A plus A. In fact, there is no B here, we are going to write it as just A only in the two compartments. So, now if you take the difference, what do you think should happen? I am going to, I have actually missed a ln here. So, I am just going to write it again, because I have missed a ln here. I will have to rewrite it again. I have missed a ln, just there is a ln here that was missing, E by rho into 4 pi m1 into E E1 plus E2 divided by n1 plus n2 whole raised to 3 by 2 half divided by 3h square here. Now, you can see E1 plus E2 divided by n1 plus n2 is the same as E1 by n1 or E2 by n2. So, the entire logarithm argument is the common argument in all the 3 terms, and if you look at the SI, there is n1 kb plus n2 kb, whereas in the denominator is the same n1 kb and n2 kb. So, if you take the difference of SI minus SF, you are going to get nothing but 0. Because of the fact that your energy density is the same as initial energy density. We have already shown this. We are mixing them with at constant temperature, and so the logarithm of argument is the same in all the 3 terms, and when you take the difference what you get is essentially 0. So, there is absolutely the take home message is that there is no change in entropy for this mixing, and the entropy did not change simply because the macro state remained at equilibrium and did not change. So, you had the same macro state to begin with and you got the same macro state when you ended. There is absolutely no way you can tell that an experiment was actually performed. Okay, when you come back, you can put a shutter back and recover the old system with the same density on either sides and the same temperature on either sides. So, clearly the change that happened in this isolated system was reversible, and for such systems, for such changes, you do not incur a change in a positive change in entropy. So, hence the entropy of mixing turns out to be purely 0. So, if you had taken in your expression for number of microstates, so I am going to talk about this expression now. Remember this n factorial which is highlighted in red color. This stands only to safeguard your computations and to make entropy purely extensive. So, if you see your entropy expression, if I scale V by lambda, N by lambda and E by lambda, the entire entropy expression is scaled by lambda, which is known as a pure extensive scaling of entropy with respect to its arguments. So, if I had not taken this care and not divided by n factorial, it would have given me an entropy which was not purely extensive, and as a consequence of that, the case of mixing of 2 same gases would have given me an entropy chain that would be positive. So, you can do this calculation, mix 2 gases of the same type at same temperature and same density using an expression for S that does not have this this correction factor, and you will see an entropy chain that is positive. I will leave that exercise as homework, and this is precisely the problem that puzzled Gibbs for a long while, and this problem is called as the Gibbs paradox. Today we resolved that paradox. We stated that there is absolutely no change in the entropy if you correctly enumerate the number of microstates by taking into account indistinguishability of the particles. So, the Gibbs paradox stands resolved. We did not encounter it because we computed the states correctly, and we shall give you one problem as homework that will so write down the homework problem. So, I am just going to state here. So, we will give you the solutions but you should do this problem yourself. So, if you take the let me copy this expression. So, the problem is in Gibbs paradox. It is a very simple thing to understand. We did not encounter it because we did the calculation correctly, but suppose you were to do this calculation incorrectly, and this is where Gibbs paradox comes. So, suppose you suppose you took the wrong expression for the number of microstates, you did not take the n factorial. Okay. Suppose you missed it, then without this n factorial, the expression for entropy, and I am going to write down a superscript to just tell you the the fact that this is a over computation. This would be just nkb. You can do the calculation without the n factorial, just take a logarithm on both sides. You would get v into 4 pi m e over 3 h square n to the power 3 half. Now, you can see that your entropy is not extensive, in the sense that if I scale n by lambda n and volume by lambda v and E by lambda E, my overall entropy S star is scaled by S original plus so this would become my lambda S plus n kb ln lambda, okay, because E by n does not matter. So, E by n remains E by n because they both scaled by lambda, and V scaled by lambda V. So, I can take n kb lambda n kb lambda, okay, and 1 lambda n kb into V into this thing is just lambda into S. Okay. So, this is the so this extra factor that I get should have been 0 if entropy was this is not 0. So, that is how I say that my entropy is not extensive. I got an extra contribution. So, and you can see this is positive in nature. because I have over counted omega. So, now if you mix to you redo this mixing of gases, take the case of 2 gases at 2 same gases at same temperature and density, and you will get you should get the entropy of mixing as non-zero. In fact, they should be, you will get it as a quantity which is positive. So, this is basically a Gibbs paradox. A little while ago when we did this calculation, we saw that the entropy change is 0, but if you do this calculation at home at at temperature and density which are same on both sides, and you mix 2 same gases, when you do the calculation in the same spirit like we did just a few minutes ago, you will find that the entropy of mixing comes out to be positive, and that is completely wrong, because it should not be positive, it should be 0. So, at the heart of the Gibbs paradox lies the incorrect enumeration of microstates, precisely because you did not take into account that there are n factorial microstates that are indistinguishable, and you over counted them and thereby made the entropy non-extensive, and hence you ran into this issue. So, we will close this lecture here, and the next class when we meet we will talk about canonical ensemble, and this is an ensemble where you allow for the energies to exchange in order to maintain constant temperature. So, we will start the next lecture from canonical ensemble and take it from there. Thank you.